Recording is rolling on Tuesday, October 19th. We're actually about a few minutes into class because you guys watched some Paul Hewitt demos, and also you guys saw some Domino's stuff. So recap those. One of the Paul Hewitts you guys saw involved a pendulum, like swinging back and forth. Okay? And hey, at the endpoints, there's no speed, so wouldn't that all have to be potential energy, like MGH? Okay? Now, one thing I told you guys yesterday is you're allowed to find the floor level, like ground zero, wherever you want. And a really convenient place to put it for a swinging pendulum is at the lowest point, because then that means at the lowest point, all the energy would be kinetic, wouldn't it? It would be all in terms of motion. There'd be no height left. Okay? So this goes potential, kinetic, potential, kinetic, potential, kinetic, but the total energy stays the same throughout. Okay? Then the Domino's chain reaction, you guys saw series of dominoes like this. Right now, of course, it takes some energy to lift it, takes some work to put it in place. And then this guy is tipped a little one, and then they all collapse. Right? He said if they had 29 of those, the biggest one would be the size of the Empire State Building. Yeah, and get all that energy back, that potential energy. Okay. All right, so quiz update. You guys turned in your quiz yesterday. Still waiting on a few, like had some absent students and stuff. So I haven't posted the solutions yet, although it's ready to. All I have to do is press a button on Google Classroom. But I did want to tell you guys that I threw out one of the questions. And it was actually one that I made a deal about reviewing with you guys too. You guys remember one that said centripetal force lab? Well, everybody got one that referenced the centripetal force lab. I said, what if you change one variable by some factor? How would that affect like, some other variable? And there is a typo here, which throws us off. See if you guys can catch it. It says, if you quadruple the weight of the hanging safety bucket from 100 grams to 400 grams, right? What's wrong with that statement? What is weight measured in? Maybe like newtons or millinewtons, possibly. Something to do with newtons. What is grams measured? Mass, right? Yeah. So I could see how you could see grams and just that could trigger in your mind, like, oh, wait, is that the mass of the swing bucket or something like that? So just because of that, I went ahead and threw that one out. So everybody got credit for that. But yeah. All right. And then I did get grades uploaded last night. So if you turned in yours yesterday, then your grade is on Focus. Right. So today, I'm going to finish the energy notes with you guys. We got a good way through, so I'll do a quick, whoops, let me zoom out so you guys can see what I'm looking at. I'll do a review with you guys what we've done so far, and then I have a few more things I have to tell you in the notes. I did promise you guys a couple weeks back that I would eventually derive escape speed. We just had to get to energy, so that'll be today. This time I'll mention, well, we'll get there, right? And then I have a new variable in unit to introduce to you guys today called power. Right? And then you guys should have on your desk when you walked in, do you have a packet that looks like this? So we'll start on this by the end of the class today. And then there's some more technical type stuff I want to do in my AP classes, so just keep everybody on sort of the same schedule. I've got a fun video for you guys at the end of class. Okay. So review of what you guys saw yesterday. There was this new concept, this new variable called energy. It was measured in joules. It's a scalar value. 1 joule breaks down into fundamental units that look like this, 1 kilogram meters squared per second squared. And then we were looking at these building blocks of energy. Well, building blocks is my kind of colloquial term for this, but what are some forms of mechanical energy? And I went through this list with you guys. So there was work, which technically is a transfer of energy. So force times distance. This is a dot product, meaning only the parallel components matter. So I gave you guys this example of the shopping cart. If you push like down and forward, only the forward part of the push actually does anything. That explains the cosine relationship, which is what a dot product is. So force times distance, but the dot product goes. So one maybe extreme example of that, counterexample, however you want to couch that, is what if you carried a book horizontally, carried a textbook horizontally across the room? How much work would be involved with that? And the answer is 0 work, because the applied force upward and the distance moved to the side, those are perpendicular to each other, so one has nothing to do with the other. There's no work involved in there. But if you lifted the textbook, okay, well, you have to do work to lift the textbook, right? And that would be force times distance because they're all in the same direction. So you push upward, you move the book upward, just multiply those together. Some number of joules associated with that. They say, okay, well, if I did that much work on the book, that means I transferred the energy into the book. Right? Hey, kind of like those dominoes that fell down. They had the energy stored in them. Okay? So the force to lift it, that's the weight of the book. The distance moved is the height. This leads straight to the next one. Gravitational potential energy is defined as exactly that, mgh. Now, caveat on this is only at a localized level, and I'll talk about that in a minute too. But here you go. Say mass of something, some height above the floor, and some gravity field, mgh. That will tell you how much energy it has, like stored potential energy, gravitational potential energy. We looked at a couple of graphs yesterday. So force versus distance. The area underneath that curve represents like work, like an energy transfer. And then another specific example, that might be going back to Hooke's law, F equals kx for a spring. The more force, the more it'll compress. What's the energy stored in the spring? Well, it's the same set of axes pretty much. So it's also the area under that curve, which is a triangle. So 1/2 base height. That leads to this formula, energy stored in the spring, 1/2 kx squared. That's what that is. Okay. I also told you guys kinetic energy is 1/2 mg squared. That's the energy associated with motion. So like that pendulum swinging back and forth had all this kind of energy at the bottom, all kinetic energy. Okay. And then we did do one conservation of energy example, which that this table, this is actually the very first example, so you guys get to see this again. Galileo drops the ball from the top of the Leaning Tower. At the top, it's all potential energy. At the bottom, it's all kinetic. Notice the setup. Sum of energy initial equals sum of energy final. This is true for a closed system. Closed system meaning there's no outside force acting on it. There's no energy entering and leaving the system. Okay. This is a way you can find the speed of the ball at the bottom. Okay. You guys know another way to find the speed of the ball at the bottom. And that's to go back to your kinematic stuff from a long time ago. Like this third setup. Okay. Physics is all self-consistent. Sometimes there's multiple ways to get to the same answer. That's what I was showing you here. Whether you get the kinematic approach or the conservation of energy approach, you get the same thing. Okay. And then, okay, here's as far as we got yesterday. I set up one more for you guys, and then this was actually a really good pause point. Going back to potential energy, that whole MGH thing. Well, MGH, if you think about it, that lowercase g, like 9.8 meters per second squared, for example, surface of Earth, right? That's really only true like at the surface of some planet. If you get too far from the surface, either way, like tunneling down or going up into space, that number changes. So there's probably some more universal type way to think about gravitation. And that's what this is. Now, I threw this at you guys, but I didn't explain it. So that's what we're going to do starting here. I'm going to explain this for you guys. Right. Why does it take that form? And that looks kind of like universal gravitation. Right? And then what's the deal with the negative sign? Something like that. Right, so there's some stuff around here. All right, so we're doing. All right, you guys remember how work is equal to force times distance, right? Dot product, but it's all in the same direction. Okay? And hey, the work you do on something, isn't that the potential energy that you give it? Okay? This could be gravitational potential energy if you're like lifting it against a gravity field. Okay? Force. You guys know a term for the universal expression for force now that you learned in the last couple of weeks. Gmm over r squared. You guys remember that? Okay? And hey, radial distance. That's one kind of distance, right? I mean, what if we're talking about the same distance here? Like you lift above, like some distance r, right? That could be like that, couldn't it? Maybe one of the r's cancels. That leaves you with, it leaves you with the magnitude of universal potential energy, which is Gmm on just plain r. Okay? But I still haven't explained where that negative sign comes from. Okay? I'll go ahead and throw it in here, but let me do my best to explain why this number is always considered negative or treated as negative. Okay? And this is really sort of like a math trick in physics, like energy counting. I mean, once you know energy is conserved and you have definitions for energy, then. So suppose we got the story of I'm going to say an almost empty universe. Okay. Let's say there's nothing in this universe except for two things. On one edge of the universe, one end, I've got a planet. It has some radial size, capital R. It has some mass m. Okay? And on the other end of this universe, there's a little tiny lab weight with some mass little m. Okay? So mass of a planet, mass of maybe it's like 1 kilogram lab weight, something like that. Okay? And these are on opposite ends of this otherwise empty void. Now, do you think there's a tiny, tiny gravity pull between these two? They're gonna pull towards each other? Yeah. And maybe they don't crash into each other until like a billion years later. Maybe that's how far away they are. It took them a billion years, starting from rest, to fall towards each other. Okay. So with that story in mind, uh, what was the energy in the system to start with? I mean, if they're like nearly infinitely far away from each other, well, you wouldn't want to use MGH for a couple reasons. One is that G gets very small, but that H would become near infinitely large, so that it's kind of hard to approach that way anyway. Okay? But maybe a good reference point is just to call this zero energy in the system. It could be like zero energy. Right? If there's zero energy in the system to start with, they're just kind of floating around, start from rest. Right? And then they start to pull towards each other. They start to gravitate towards each other. Well, the planet's not going to move that far, but the lab mass is going to move like across the universe. Right? Then, as they're moving towards each other, aren't they gaining kinetic energy, especially lab mass? It's like picking up kinetic energy falling from the edge of space. But hold on a minute. I told you guys that energy was conserved. So if it started with 0 joules of energy in the system, then it's gaining kinetic energy from that. Where's that energy coming from? Well, it's coming from potential energy, because something falling towards something, you lose potential energy as you pick up kinetic energy. So that means, here we go, that if you start with 0 energy, and then you lose potential energy from that, that's why potential energy in this context is always treated as a negative value. Okay? It's always going to be negative. That's what I do. Okay? And this is also going to help explain, this leads right into explaining escape speed. Okay? And I'll show you guys why. Okay? So let's do a conservation of energy setup. Sum of energy initial equals sum of energy final. Okay? And I told you guys we're sort of defining it this way, thinking this way, is that these two objects at the edge of space have like 0 joules to start with. Okay. Then the lab mass starts falling towards the planet. The planet moves a little bit too, but tiny bit. Okay. There's some kinetic energy and there's some potential energy, K plus U. Okay. Ooh, okay, so 0 joules of energy. Let me sub in some formulas. I know kinetic energy is 1/2 mv squared. And potential energy, well, it's this negative value, negative G M M on R. Could be like that. Okay. Now, where can I go with this? You know what I could do is, when this lab mass eventually crashes into that planet surface, isn't it some distance, capital R, from the center of that planet? Okay. I'm going to go to that point. I'm going to say, here's my initial state, here's my final state. I mean, this looks generic right now, but I can change to a specific location if I change this generic lowercase r to a specific capital R to represent the radial size of the planet. Is that true? And that means that this speed right here, this v, would represent the crash speed. Okay? This would answer the question. If something fell from the edge of space, how fast is it going to crash land on the surface of a planet? Okay? Now, if you didn't know physics or you're trying to like throw around possibilities in your mind, you might wonder, I mean, if something falls from the edge of space, like the edge of infinity, does that mean it's going to be moving infinitely fast? That's a good thought, if you have that thought. But actually, it's not infinite. It's finite, and we can solve it right here. Just solve for v crash. So add the potential energy term over, get 1/2 m v crash squared equals G M M on R. Okay. Oh, what's going to cancel on both sides? Yeah, the little lab mass. Right, so as long as it's small compared to the planet. And cross multiply the 2, take the square root. Looks like v crash. Right, here's how fast anything's going to crash land falling from the edge of space. 2 G M on R, and then the square root of that. Okay. Oh, square root 2gm on R. You guys have seen this before. Where have you seen this? Isn't that escape speed? That is escape speed, isn't it? Because I saw this in terms of like how fast it's going to crash into the planet falling from the edge of space. But if you turn this around, isn't the mirror image of this also true that you would also need the speed? Say if you were at the surface of the planet and you wanted to throw this lab weight straight upward, so fast that it was able to go to the edge of space before it came to a stop. That would be the same speed. It's just like this in reverse. So that's escape speed. Escape speed is square root 2gm on r. So that's that derivation. So, and remember, orbital speed is just square root gm on r. All right. Let me just show you some notes that I was showing in my AP class, which is, remember, negative GMM on R simplifies to MGH just for a local level, right? So I'll just go through this with you guys real fast, right? So why does negative GMM on R simplify to MGH at a local level, right? Suppose you have a planet and there's like a mountain and a valley, right? And you drop something from the mountain level to the valley level. See these dash lines? That's a like difference in altitude. Now, difference in altitude between this R1 and this R2, I'm going to call it H. So H is R2 minus R1. Okay, well, the change in potential energy would be the potential energy at R2 minus the potential energy at R1. Okay? Of course, you got negative terms, don't forget that. Get a common denominator, looks like this. Okay? And then the next step is to say, well, you could factor out the GMM from the top, and that would make it look like this. Okay? Then, if R1 and R2 are pretty close to the radial size of the planet, which they definitely are in this picture, right? Capital R, R2, and R1 are, I mean, they're different, but not that different. They're about the same thing. Okay. Couldn't you say that you could do the type substitution? Okay. Then GM on R squared, you guys have seen this before. This is the gravity field of a planet. You sub that in, it becomes exactly MGH. Okay. And so that was kind of deep. I'm not going to quiz you guys on that or anything, but fun adventure there. Okay. All right, let's talk about power. So new variable with a new unit, new concept, power. This is a rate of work, or you could say a rate of energy transfer, because that's what work is, right? Work is an energy transfer. Okay. So power is, well, you guys know what rate of means, right? It's just that term divided by time. The rate change of displacement is velocity. Rate change of velocity is acceleration. Rate change of work, that's work per time, is power. Okay. So something to do with that. And power is measured in watts. Now watts, capital W, I think you guys are familiar with. You guys have heard of watts. If you look on a light bulb, draw a little light bulb here. On the top, it might say something like a 40-watt light bulb, 40 watts. Right? Oh, now you know what that means. That means it's that light bulb is pulling off energy off the grid at a rate of like 40 joules per second. Right? That's what one watt is. 1 watt is the same thing as 1 joule per second. Right? I mean, work per time, joules, seconds, 1 joule per second. Right? That's, yeah, there you go. That's the rate that light bulb will pull energy off the grid. Right? 1 watt. Then in terms of fundamental units, well, you guys remember joules is newtons times meters. In a newton is kilogram meter per second squared. So if you go down to the fundamental unit level, 1 watt is the same thing as 1 kilogram meter squared per second cubed. Right? So this light bulb, this 40-watt light bulb, is pulling energy off the grid at what rate? At 40 kilogram meter squared per second cubed. Right? And there's some power plant on the other end that's producing power at some rate. That could be quantified like that too. Okay. Now there's a funny thing you can do with power. You can actually get an alternate form for power. I said work per time, like a rate of work, right, or energy per time, something like that. Yeah. What I'm going to do is take this definition, work per time, and you guys remember how work is force times distance? Okay. So we're going to rearrange that, and I'll get a different formula for you guys for power. So sort of the definition way to think of it is exactly what's up there, right? Work per time, right? Rate of work. Okay. So what if you did this? What if you say power is work per time, but that's the same thing as work is force times distance times t. Like that. Now, if you wanted to combine some of these variables, well, one way to do it is just to go backwards, say, let's combine force and distance. Oh, that's work, and it just looks like that. But another way you could organize these variables is, hey, what is distance per time? What's that called? Is that like speed or velocity, right? Isn't that what that is? Here is an alternate formula for power. Force times velocity. Force times velocity. Right? For example, suppose there was an elevator. An elevator going. Let's do free body diagram on this elevator. FBD, free body diagram. Okay. So this elevator has a center of mass. This elevator has a weight that's pulling it down, mg. Okay. And maybe like a tension force from a cable pulling it up. So F sub tension, tension force. Okay. And the way I just drew this is those are equal magnitude, which means that this elevator is in equilibrium. So it might be at rest or it might be moving. Let's say it's moving. If it is moving, it's moving how? With constant velocity, okay? Because the force is balanced, so there's no acceleration. Okay, okay, so let's suppose that there's a motor at the top of this elevator shaft, okay, and it's pulling this cable up. It's pulling the whole elevator up at constant velocity. Okay? Hey, does this motor need some energy input? Yeah, right. I mean, it's got to be running. It's got to be connected to the grid. I wonder at what rate is it pulling energy off the grid? Oh, well, that's exactly what this formula would answer, wouldn't it? Okay. It'd be the tension force multiplied by the upward speed of the elevator. There you go. You just multiply the two together. So this tension force feeds in there, the speed feeds in there, and then you can get the rate that the motor pulling that elevator up is doing the work. Okay, good so far? All right, let's look at this table. So we're on time. I've got till 14. All right. So you guys see this table right here? Let's do at least a couple of these, and then okay. All right, so I've got for you guys lots of different scenarios. There's a few pages of these, right? And actually the very last one, in case you hadn't noticed, was a bunch of conceptual questions again. Right. So there's, let's see, a bunch of different scenarios. Next column says, what is in the closed system? Closed system just means a system that does not have any outside forces acting on it. There's no energy transfer into or out of. Okay. And if the system is closed, that means that the energy at point A and the energy at point B, well, you must be able to equate those because energy is conserved. Right? And then you can do stuff like solve for stuff. And this is the layer deeper that, like when Paul Hewitt was talking about the pole jumper example, you could go the extra step of saying like solve for, what's the speed that he's crashing into the bucket cloud, something like that. So that's this last column. All right, so the first example, Galileo drops a ball from Leaning Tower. Right, this one, well, it's a good start example because you guys have seen the story many times. What is in the closed system? What do you guys think I should include? Drops a ball. We're watching a ball move, so I mean, we've got to include the ball, right? Okay. I need to include one more object in the system for this to work. Okay. Guess what force is pulling the ball? Gravity, supplied by the presence of the Earth. Right? The fact that there's a big old Earth there with a big old mass. Right? Those are the two objects in the system. That's all I care about. The ball and the Earth. They're falling towards each other. Well, but the Earth is so massive that it falls. You see that motion. Right? What kind of energy at point A? Now, if ball is just holding the ball at rest at the top, then isn't it all potential energy? Can they call it MGH? And a little subscript A on that H. Just match that one. Then, what about at point B? Now, some of these you have to sort of read between the lines, or sometimes there's multiple ways to think about it. But let's say at point B, this ball is like a millimeter above the ground. It's moving really fast. It's got some V final, or I should say V sub B. Wouldn't it all be kinetic? All 1/2 mv squared? The little subscript B on that V? Okay. Because the ball has no more height at that point, so it has no more potential energy. It's all kinetic. Okay. Then solve for the speed at point B. So, now this last column, I should tell you guys this. You might want to write above this column, this setup. Sum of energy at point A is equal to the sum of energy at point B. Because that is the setup for every single one of these. That's the whole premise of this table, is conservation of energy. That's what that says, energy is conserved. So the sum of energy at point A is equal to the sum of energy at point B. Okay, so for the Galileo example, energy at point A is just mgh at point A. At point B, it's all 1/2 mv squared. At, of course, point B. And then since the last problem says solve for VB, then okay, let's do that. Let's do some algebra and finish this out. Get that one, that variable isolated. Oh, what's going to cancel on both sides? Yeah, the math, which should be no surprise because that's been the story all along. Right? I mean, physics is always internally self-consistent, or should be. Cross multiply the 2, so I'm getting VB squared equals 2GH. Take the square root. There you go. And you guys have seen this a few times before, including yesterday. So, okay, so that's all good. Okay. So, yeah, I did make this last cell way too small. So that's why I'm doing this on the paper. But the answer is square root of 2GH. Okay. Okay. Is that right? All right, next one. A cannon fires a cannonball at some angle from ground level. Okay. Now, point A is after it's already left the cannon barrel. I mean, maybe just barely, but it's got some V sub A at that point. Okay. And point B, well, maybe it's like, maybe, I don't know, the highest point is trajectory, possibly. It's somewhere in the sky. Okay. Let's say it's the highest point, so it has like horizontal velocity, like VB. Okay. Just like that. Okay. Now, this is another one of those, just like the first example, that you could use solving kinematic formulas. Maybe you want to double check the answer doing that. Okay. Now, this would be a projectile problem. So you've got 2 dimensions to think about. You have to do X dimension, Y dimension. But, okay. But here's another approach. Okay. What's in the closed system? I'm thinking the same objects as before, sort of. We got the cannonball. That has to be part of the system. It's in motion. I mean, it has V velocities. It's going to have kinetic energy, so that has to be. Okay. I have to include the Earth because the Earth is changing the motion of the cannonball by pulling on it with a gravity force. Okay. And that's it. Okay. Now, you might have said, wait, should I include the cannon? Well, if you went back like a few seconds, like as the cannon is blasting the cannonball, maybe you could make a case for that, but I'm just interested in just after that cannonball's left the nozzle of that cannon. So just that. What is the energy at point A? Well, see how I define ground level as where it's leaving the cannon? So that means there's no potential energy and it's all kinetic. It's all 1/2 mv squared at point A, like leaving the cannon. Now at point B, it's really an energy mix. It does have some kinetic motion. I mean, it is in motion at point B. It's not moving as fast, but it is moving. So there's some 1/2 mv squared, the little subscript B on that B. And it's also acquired some height in the process. So that's mgh sub B. In fact, the higher it goes, the more energy is being diverted into potential energy. Probably the slower it's going. That makes sense, right? It's going up, it's going slower. Now, the old way of thinking about that was that it'd be moving up and accelerating down. That's why it slowed down. The new way of thinking of it is that more energy is being diverted into potential energy, okay? But the end result's the same. Okay. So what is the speed at point B? Okay. Well, let's set this up. Sum of energy at point A is equal to the sum of energy at point B. Okay. Now, point A, it's all 1/2 mv squared at point A. Okay. So we're V sub A is blast speed of the cannon. At point B, well, we have this energy mix. We got some 1/2 mv squared left over, but a lot of the energy was diverted into mgh. I guess throw a little subscript B on that. Okay, so let's go solve for B, or sorry, V sub B. Do you guys see the mass of the cannonball is going to cancel again? No surprise there. Okay. Shuffle some stuff around. Take the GH, move that over. So 1/2 VB squared equals 1/2 VA squared minus GH sub B. Multiply everything by 2, take the square root. V sub B is square root of, it's going to be V sub A squared minus 2GH sub B. So that last step has a couple of algebra steps in it, but that's what that would be. Okay. So that's the answer. It's V sub B is equal to a big old square root, VA squared minus 2GH. Okay. Now, whenever you get an answer, it's a good idea to pause, reflect on it, say, does this make sense? Okay, for example, what if this cannonball came back down to ground level, which it eventually will, and in a general sense, you might even assume that was the case. That, I mean, HB could be 0, couldn't it? If the cannonball comes back down to ground, wouldn't HB this height be 0? Okay. If that's true, well, let's see how this would play out. If this height's 0, this term goes away, and we have the square root of VA squared. Isn't that just V sub A? So VB would be VA. Hey, that's also consistent with stuff that you already know in this class. So at equal elevations, it's equal speeds. And then what's it, the higher it goes, well, you're subtracting from that, so it'd be slower and slower. Ooh. One more thing. You could have solved this from a different point of view. So if you go back to projectile motion from a few weeks back, you could have said, well, this cannonball was blasted at some angle theta. And I know that V sub B is the same thing as the horizontal component of that speed. So you could have said this. You could have said V sub B is equal to V sub A times cosine of that horizontal blast angle, right? Or blast angle from the horizontal. But these are the same thing. And if you had some numbers, you could go and confirm that with the same thing. All right, guys, all right? All right, so here's what we do. We're gonna pause right here. We'll do a lot more of these tomorrow, but we're gonna end class today on a fun video on Olber's paradox. Olber's paradox.